All right, good morning, everybody. So we've been talking about functional groups, and we started talking about where X is not a halogen necessarily here, okay, it's just a variable. We started talking about the fact that there are numerous functional groups that contain the carbonyl. What can X be, and then what are the corresponding functional groups? So X could be a hydrogen, and if X is a hydrogen, what would the functional group be? It's an aldehyde, right? What else could X be? Pardon? Another carbon. Okay, so we'll just write it as R prime. And so if we have that, then what is the functional group? A ketone. What else could X be? OH. And what would that be? What else could X be? Pardon? Okay. So it could be a nitrogen. And I'm going to put R2. So two different R groups, which could either be hydrogen or whatever. And what would that be? An amide. Right? And we can have primary, secondary, and tertiary amides depending on how many carbon bonds to nitrogen. What else could X be? Could be a halogen, could be a chlorine, and if it's a chlorine, then it's a acid chloride. What else could X be? OR. And there we would have what? An ester. Okay, so there's a lot of carbonyl containing functional groups that are present, and there are actually others that we'll learn later on, but those are the good ones for right now. So I give everybody a molecule, and I tell you that each molecule has a different functional group. How would you determine what functional group you had in your molecule? If I gave you all a sample, and I told you to go in the lab and figure it out, how could we figure out what functional group we have? What technique would we use? We'd use infrared spectroscopy. Okay? Infrared spectroscopy is a very, very powerful tool, but it's mostly useful in the identification of functional groups. It can be used for other things, but it really has its power as a functional group identification technique. So if you have a molecule and you're sitting there going, well, with this molecular formula, it could either be an alcohol or an aldehyde, this technique will tell you the difference. Okay? It's a very, very powerful technique. When you hear the word infrared, what do you think about? Light, energy, what else? Waves, light waves, what else? Yeah, okay. What else? How about heat? You all ever go to a fast food restaurant and they've got all the burgers and stuff under those heat lamps? People call them heat lamps, but actually they're infrared lamps. Okay? So really what we're talking about here is heat energy. And heat energy makes things vibrate. And we can use those vibrations to determine functional groups, because it turns out that each functional group has a characteristic vibration when it absorbs heat. And we can, with a little bit of practice and good puzzle solving skills, usually figure out what functional groups we have in a molecule using this technique pretty conveniently. So we're talking about the electromagnetic spectrum. I think I heard somebody talk about waves and energy and all that, and that's what the electromagnetic spectrum is, right? And so if you've had physics, you kind of know this. You've got everything from cosmic rays all the way to radio waves, right? And all this is part of the continuum of this electromagnetic spectrum. Which ones are the high energy? Cosmic and gamma rays, very high energy, right? What about radio? It's low energy. And where is IR in there? Yeah, it's kind of close to the radio. It's kind of in the low energy region of the continuum, right? And so this tells us a little something. It doesn't take a whole lot of energy to make a molecule vibrate, okay? And especially a functional group. And so there's a part of the infrared, or part of the electromagnetic spectrum that is the infrared region, which is where kind of the heat is, if you will. I do not care for organic chemistry if you know the value of Hertz for all this, okay? Just know that it is on the low energy side of the electromagnetic spectrum, okay? We're talking about heat, okay? So, with high energy, okay, things like gamma and cosmic rays, we're talking about the ability to ionize molecules. That is, knock electrons completely out of them. Over here at the radio wave, all we're able to do is take a nucleus of an atom and actually get it to flip. Okay, that's actually what MRI is. For those of you who are interested in medicine, we'll talk more about that in chapter 9, I believe. But kind of in this region is where we're talking about infrared, and really the infrared radiation is going to have vibrations and rotations, and that's what we're going to be dealing with. And in the IR spectrum itself, we're dealing solely with vibrational energies. Okay. So, infrared spectra we're going to be dealing with, they are recorded by passing a broad spectral range of radiation, of IR radiation, through a sample, and noting the wavelengths that are absorbed, and the pattern of the wavelengths that are absorbed gives us structural information about the compound. So let's think about that. If I have a molecule and it's static, and I put some energy in it and it starts to vibrate, what happens to that energy? If I've got heat energy coming in, striking that molecule, and it starts to vibrate, what happens to some of that heat energy? It gets absorbed. That's exactly right. So if I know how much energy I'm putting into the molecule, I can measure how much comes out, right? And the difference must be the amount that's absorbed, right? Which is proportional to the vibration. It's all quantum stuff, okay? And fortunately, in organic chemistry, we don't have to do a lot of the quantum stuff, okay? Now, an IR spectrum, at least that we're going to be dealing with, typically you have what's known as percent transmittance on the y-axis. You can also have it listed as absorbance, but in this class we're going to focus on transmittance as a percent. And then on the bottom, on the x-axis, we have what's known as wave number, which is in the units of reciprocal centimeters, okay? And so ignore this top scale. There are still some people that report it this way, and some people that report it as absorbance, but we're not going to do that in this class. We're going to focus on percent transmittance and wave number. So if I have a molecule that doesn't absorb any of the infrared radiation, the percent transmittance would be what? It would be 100, right? Because it's how much is transmitted, right? So if I put in, let's say 100 joules of energy, I get 100 joules out, 100% of it was transmitted through the sample, okay? So if I have a molecule that has a functional group, though, that strongly absorbs the IR radiation, the percent transmittance would be near where? It'd be getting closer to 0. That's right. Rarely does it go all the way to 0. Sometimes it does, but it would certainly approach it. This is what an IR spectrum could look like. What do you see? You see peaks, right? And they're pretty broad, right? They're pretty wide for the most part, okay? And can you tell me what molecule that is right now? No. But I promise you, with practice and the lab that you all will be doing in the next week or so, you all will be able to look at IR spectra, and at least if given a list of potential candidates, you'll be able to identify the correct one, okay? If you like working with puzzles, you're going to love this, okay? Because these are pieces to a puzzle, and you put the puzzle together to give molecular structure, okay? And so you're going to learn how to take spectra that look like this and determine which molecule is the correct one, okay? There we go. All right, we don't need to really focus too much on that. Let's think about this for just a moment. I've got two atoms that are connected together by a bond. Two atoms have a mass, right? So we can treat those as weights. What's the bond treated as if it vibrates? A spring. That's exactly right. And so if you've had physics, you know that two masses on a spring can be described by Hooke's law. And so this simple physics experiment can actually be applied in chemistry, and we can determine structure from using this thing called Hooke's law. Okay? So we can think of two atoms connected to each other by a bond as two weights on a spring. And if you've ever looked at Hooke's law before, you know that there's going to be a force constant that's related to kind of the stiffness of the spring. So if we have a single bond, we can have a double bond, and we can have a triple bond, for example. How's that stiffness going to change? Yeah, right. So we know that pulling a double bond is going to be a little harder than pulling a single bond, and a triple bond is going to be harder to pull than a double bond, right? It's kind of the same concept as if you took a rubber band and put on both of your fingers and you stretched it, right? That would be like the single bond, and then you wrap two rubber bands around it and you tried to stretch it. You would be able to feel that, hey, I got to pull a little harder, right? And then if you took three rubber bands and put around and you tried to stretch, you would notice that it was a little harder to stretch. Same kind of relationship here. Now the mathematical relationship for Hooke's law looks something like this, okay? So the frequency of the absorption, or the wave number if you will, okay, is proportional to this. Notice the force constant is there, and this is known as the reduced mass, the mass of the atoms that are involved, okay? You will need to be able to derive this on the exam. No, you won't need to be able to derive this on the exam. Everybody started literally looking at me, all right? You will not solve this equation in this class. What I want you to know is that the frequency of the absorption is proportional to the force constant, okay? That's a really complicated way to say that, okay? It's very important if you're a theoretical chemist, because you will actually use this to determine what these frequencies can be if you know what atoms you're dealing with. And so I actually have some software that I can draw a molecule and it will predict the IR spectrum for me. And the prediction's actually pretty good, but it uses Hooke's law. So it goes through and it looks at the atoms that are connected together, and it knows, hey, that's a single bond, so I know what my force constant is, and I know what atoms he's put in there, so I know this, and they can predict that. And it comes out pretty close. Hooke's law works pretty darn well for this. Huh? Force constant, right? Well, actually the square of the force constant, but who's a mathematician, right? So that's what I want you to know, okay? When you get into, how many of you have had physics? Okay, a couple of you have had physics. When you get into physics, you're going to solve Hooke's law, okay? You can figure all that out there. What I want you to do in this class is use Hooke's law, okay? And so basically, this is telling us the energy, that frequency of that bond vibration is the frequency of the energy that has to be absorbed. And that comes from quantum physics. Not just any old energy will make a bond vibrate. It has to be the right energy, okay? And that's why we can get some really telling information from an IR spectrum, okay? So the way to think about this, again, is like two masses connected by a spring, and we have the low energy vibrational state. We put some energy in, and that stretches, right? And so we can see stretches. But is stretching the only thing that I'm limited to? No, I can also bend bonds, right? As we call them, wagging. So we can stretch, we can wag, and they can do a bunch of strange things. And on Monday when we come in, before we do the inverted lecture, I'll actually have my software and I'll demonstrate what some of these vibrations actually look like. And some of them are kind of humorous. They look like they're little dancing people, okay? And it's kind of cute. But we can use that information to determine structure again. That's the thing. All right. This is kind of the general region that you need to pay attention to in infrared spectroscopy. I'm going to teach you a couple of simple laws, my laws, okay, for interpreting an IR spectrum. All we're interested in is what? the functional groups. Okay, so if you look at those regions up there, what do you see? You see a functional group region, you see a fingerprint region, and you see an aromatic region. And I told you that for the purposes of this class, all we're interested in is the functional group region. So when I give you an IR spectrum, where are you going to start? But where are you going to start? Where are you going to draw a line and say, I'm going to pay attention to this, and the rest of it I'm going to ignore? 1500, that's right. First law, you start at 1500. So anytime you get an IR spectrum in this class, you will start at 1500, and you will either draw an imaginary line or a real line. Well, there's always going to be some fuzziness, but we're going to start right here, and we're going to ignore everything to the right. Now, in sapling, you will have a few problems that will ask you to interpret stuff over here, and you'll have to look those values up. That's okay. I want you to understand how complicated the fingerprint region is. The fingerprint region is where you find single bonded stuff. Carbon-carbon single bonds, carbon-oxygen single bonds, carbon-chlorine single bonds, and guess what? Organic molecules have a lot of sigma bonds. So this region is extremely complicated. It can be interpreted, and you will at some point be able to interpret it, but not today, okay? So this region can get really complicated. So if this is the single bond region, how else could we label that? Sigma or sp3. Notice it goes sp3, sp2, sp. Real easy to remember. The fingerprint is sp3, sp2, sp, and the hydrogen region, okay? Now, you start at 1500, and then you just move in steps of 500. So Sarah would start at 1500, and she would simply take a step to the left 500 units and draw another line at 2000. Between 1500 and 2000 is the sp2 region. That's where you're going to find carbonyls, carbon-carbon double bonds, carbon-nitrogen double bonds. You're going to find all your carbons that are sp2 hybridized in that region. Now we're at 2000. We take another step of 500. 2500, we draw a line. So between 2000 and 2500 is the sp region. This is where you're going to find things like carbon-carbon triple bonds, carbon-nitrogen triple bonds. Anything that's sp hybridized is going to be there. Where will you find carbon dioxide? Is it sp2? How many pi bonds are involved on that carbon? So what's its hybridization? It's sp. So where am I going to find carbon dioxide? It will actually appear in this region. You will see it when you go into the lab and actually run a blank, because air contains carbon dioxide. You'll see a little peak always around, I forget exactly where it's at, but in that region, and you're going to blank it out because you're running your experiment in air and you don't want to see the carbon dioxide, but it's there, okay? 2500 and beyond is called the hydrogen region. This is where you're going to find hydrogen attached to stuff. OHs, NHs, and CHs. Okay? So let's repeat the rules. Where do we start? And what step do we take, and in which direction? 500 to the left. That gets us to 2000. Then we take another 500 to the left. And then beyond that is the hydrogen region. Okay? IR interpretation is just that simple for functional groups. Okay? You need to know those regions. I would highly recommend that you not use your note card on an exam for the regions. Okay? I will not give you anything on an exam that requires you to know to within a few wave numbers. If you know the rough regions, you'll be able to interpret things for an exam. Okay? So, let's look at some characteristic frequencies. So let's look at carbon-hydrogen bonds. Alkanes, alkenes, and alkynes. What can you tell me by looking at that? The force increases, right? That makes sense, right? Because a triple bond should be harder to stretch than a double bond. And notice where the energies are. They're not identical, are they? They're not all at the same location in that hydrogen region. We're going to find alkanes around 3,000 to 2,850. We're going to find alkenes, right, a little more to the left of that. And we're going to find alkynes just a little bit more to the left of that when we look at the spectrum. Okay? So, carbon-carbon bond stretching, what would you predict? We would expect to find this in the fingerprint region because it's single bonded. This in the double bond region, this in the triple bond region. Again, the increasing force constants. Okay. Carbon-nitrogen bonds. Where might we find a carbon-nitrogen single bond? Yeah, kind of in that fingerprint region. A carbon-nitrogen double bond, we're going to find it in that sp2 region. A nitrile, we will find that in the sp region. Okay? And so in your book, you actually have a list of these infrared absorptions. You know, so if you've got molecules that are really similar, you can get down to the nitty-gritty and look at the exact regions where these things absorb, right? You're going to need to be able to do this in lab. That's where you'll get your practice at this, right? In lab, you'll do a number of IR spectra. Notice that an aldehyde and a ketone both just have a C double bond O, right? But notice that the stretches aren't exactly identical. They're really close, right? But they're not identical. So if you didn't know this right off the bat, how might you distinguish an aldehyde from a ketone otherwise? Yeah, but you're not going to be able to smell it on an exam. I'm not going to spill it on the exam, right? So let's say Yusuf forgot that an aldehyde actually absorbed just a little bit differently than a ketone. He sees that there's a carbonyl, but he can't distinguish between the ketone and aldehyde. What else might he use in the IR spectrum to determine? What's different between an aldehyde and a ketone? That's an aldehyde, right? That's a ketone. So what can he use to determine whether he had an aldehyde or a ketone? You could, but that's down in the fingerprint region. Harder to interpret. Yeah, but that's not going to be in the fingerprint region. That's going to be in the functional group region, right? So he'd be able to see this particular hydrogen stretching on the graph. You'd be able to determine that. Okay? So let's look at some structures. Octane. Predict for me where you're going to see everything. Before I throw it up there, where are you going to see absorptions on the IR spectrum? We're going to start where? 1,500. Am I going to see anything between 1,500 and 2,000? And why not? There's nothing that's sp2 hybridized. Am I going to see anything between 2,000 and 2,500? No. Am I going to see anything between 2,500 and 4,000? You bet. I'm going to see a bunch of hydrogens, right? And is my fingerprint region going to be, am I going to see something there? Yeah, but I'm not going to be able to interpret it too well, right? And so the spectrum actually looks something like this. Notice starting at 1,500, this is the fingerprint region. There's all kinds of stuff going on here. And then notice out here between 2,800 and 3,000, we have this nice, strong absorption. That's typical of what an alkane looks like. Okay? Now, let's take an alkene. How is that going to differ? It's got a carbon-carbon double bond, so where am I going to see something in addition? Okay, I'm going to see something in the sp2 for sure that's going to be different than what I'm seeing up above. Where else am I going to see a difference? What do you mean by lower absorption? Okay, that could be. That's true. What about the hydrogen region? Notice I pretty much so just have this one blob, right? Do I only have one type of hydrogen here? I have carbon that's singly bound to carbon, which is sp3. So I have hydrogens on sp3 hybridized carbons, and I also have hydrogens that are on what kind of carbon? sp2. So am I going to see a different set of peaks for those? You bet. To the right or to the left? To the right or to the left? To the left, right? And in fact, that's what we see. Again, notice starting at 1500, this is all fingerprint. Notice I see something here. It's fairly weak. It's a carbon-carbon double bond. Why is the carbon-carbon double bond weak? That doesn't go all the way down to 0. Why isn't it absorbing a lot of radiation? How does IR work? In your reading, what did you determine? What has to change for IR to work? Dipole moment. That's right. So for IR to actually work, the stretch or the vibration has to result in a change in the molecule's dipole moment. If that doesn't happen, it doesn't show an absorption. Okay? That's one of the rules for IR. So if I've got a carbon and I stretch them, is there a huge change in dipole? Why not? Because they're the same electronegativity, right? So I don't have a huge change in dipole moment. That's why I don't see a huge absorption. Is there a change in dipole? Slightly. Because a CH2 is clearly different than a C connected to an R. And so there is slight electron differences there. And when you stretch it, there is a slight change in dipole. Okay? So again, tying together why we were talking about polarity the other day, it's kind of important here for IR. Notice what we see in the hydrogen region. We see this additional peak out here just to the left, which are the hydrogens attached to the sp2 hybridized carbons. Just a little bit, right? Now we've got a triple bond. How is that going to differ? Okay. Again, starting at 1500, right about there. We're going to ignore all that. Notice from 1500 to 2000, I've got nothing. Really? There's a little blip there, but that's really nothing. And then I've got from 2000 to 2500, I've got this absorption. What's that? That's the carbon-carbon triple bond. And notice it's not very strong because carbon and carbon have the same electronegativity. But now notice, now I got a huge peak here, right? Why is this peak so strong? Yeah, so if I'm stretching that carbon-hydrogen bond, right? Are carbon and hydrogen identical in electronegativity? No. And so we see a much stronger absorption. Okay? I promise you, after practice, and you will be able to look at these and this will all start to make a lot of sense to you. You'll actually be able to look at an IR spectrum and be able to predict what the molecule is. Okay? Or at least eliminate molecules. Okay? Now let's look at some other functional groups. Let's look at Butyl Alcohol. What can you tell me about it? Not the spectrum, but what about the functional groups? Where are we going to see stuff? Right? We're not going to see anything in the sp2 region. We're not going to see anything in the sp region. And in fact, it's pretty blank right here, right? There's really nothing there. Here I see CH stretches that are due to these sp3 hybridized carbons. And notice what I see for the OH stretch. Describe that to me. It's broad. What else about it? Okay. What else do you notice about it? It's just one what? Okay. If you were in math class, how would they describe that curve, that shape? Kind of like a parabola. It's very parabolic, right? It's symmetrical for the most part, right? It's a fairly symmetrical but broad stretch out here around 3,300, okay? So wait, 3,300, that's about where an alkyne also appears, right? We saw that in the previous slide, but how do I know that that's not an alkyne? Because it's broad. That's right. So the shape of the peaks are going to be as important as the location. So you need to commit these things to your knowledge as well, right? So if you just went, well, I know 33 is an alkyne, 3300 is an alkyne, and oh, that must be an alkyne. No, you haven't taken into account the shape.
So an alkyne would be more like a jagged.
It's more sharp, narrow, right? But if you had forgotten that, and let's say you said, oh, that's probably an alkyne, you better be looking for something else as well. What? Something in the sp region, the carbon-carbon triple bond, and there it isn't, right? So immediately you know that it can't be an alkyne if you've forgotten that an alkyne can't be as broad as an alcohol. And so what you notice is that the OH has a similar shape regardless of what it's attached to, right? This is benzyl alcohol, right? It's a little fuzzier, but you can still see that broad spectrum. You can see the carbon-carbon double bond stretches in the region. This is a bad background. There's really nothing there. Okay. We're going to talk a little bit about sample handling because you're going to need to do this in lab. Fortunately, most of the stuff that I'm going to tell you in here we no longer do. I just want to give it to you for historical reasons. Okay? IR for you all has gotten so easy. When I was in school, I would have killed to have the IRs that we have today. Okay, so we had to go through all this sample handling stuff. Okay, usually you record infrared spectra either as thin films or as solutions in liquids that don't absorb a whole lot of infrared radiation. And we used to have to use these things called cells. And we would actually make a solution. We'd put them in these cells. And these cells had to be made of a material that didn't absorb IR radiation. Well, it turns out that salts don't absorb IR radiation very well. So these cells were made out of sodium chloride, potassium chloride, or even silver chloride. Now, salt doesn't sound very expensive, right? But a single salt plate that we used to buy was $100. Okay? They are single crystals, huge single crystals of salt. They're about that big around. They're not like they just take salt and just pack it together, okay? What do you know about salt? What does it like to dissolve in? Water. What does the air have down here in the south? A lot of water, right? So you can't just leave these things out on the bench or they start to dissolve, okay? So there's $100 worth of salt getting ready to dissolve into 2 cents worth of salt, right? And so you have to store them in a desiccator that keeps the water away. And then we would give these to students. So we used to actually have you all do this. And we'd give you all these salt plates, you know, and your lab fee dollars were buying these salt plates. And we'd say, go clean off the salt plate. Well, inevitably, when you've got 180 students, what did they do to go clean it off? Oh, let's wash it off. No, right? So that's bad. Okay. Today, you actually use what's known as a diamond anvil. The little dot that you'll see on top of the IR spectrometer in the lab is actually a piece of diamond. Diamond does not absorb very well infrared radiation, and it doesn't dissolve in water, which is kind of nice, right? So even though, yes, you pay an awful lot for that piece of diamond, it's really robust, okay? Solvents that we used to have to make these solutions in, we had to have solvents that were fairly transparent to infrared radiation, and so the one that we almost always liked to use was carbon tetrachloride. Yes, it has polar bonds, but it's overall nonpolar, so when we stretched it, what happens to the dipole? Nothing, right? And so it gave very few IR absorption, so it was a fairly clean solvent to use. We used to use that a lot when I was in undergraduate school. We no longer use that because carbon tetrachloride is a potent carcinogen, as we talked about before. Carbon disulfide is a pretty good solvent as well. Unfortunately, it has a habit of spontaneously combusting, and so students would pour this into a beaker, and all of a sudden they'd have a flame. Okay, and that's not good. It's kind of fun, but it's not good. These are the types of questions you might expect to see on an exam of mine and on the ACS standardized exam. These problems come directly from the ACS study guide. You're more than welcome to buy a copy of it in main office. I think they're charging $22 for them. So here we have a choice of compounds, and you have a spectrum. Now you have to identify which spectrum, or which compound, excuse me, belongs to that spectrum. So what are we going to do, Sarah? Where are we going to start? We're going to start at 1500, right? And we're going to draw a line here, and we're going to ignore all this, right? Amber, where do we start after that? So if we start at 1500, now what do we do? Go to 2000. We're going to take that 500 step, right? Do I see anything there? Yeah, so I know that there has to be something that's sp2 hybridized. Can I eliminate anything based on that information alone? I can eliminate A. And you know what? Elimination is sometimes better than knowledge, especially if you're going to be a physician. Because rarely will you ever know what made your patient sick. But you need to be able to accurately eliminate what it isn't. Okay? So you have a patient that comes in, they're sick. You don't want to give them an antiviral if they got a bacterial infection. You may not know what the bacterial infection is, but there is a set of antibiotics that you know will work on the bacterial infection, right? So elimination is an important skill to have, especially in the medical field, okay? So we're going to eliminate A. There's nothing sp2 hybridized. Everything else has something that's sp2 hybridized, right? Okay? Now, what other step do we take? Keep moving left. Do we have anything there? No. So that doesn't, and nothing has, I can't eliminate anything either, right? And so now I'm in the hydrogen region, right? And I see some CHing around 3000, a little to the right of that, right? Can I make a decision based on that? Okay, so I don't have an OH for D, right? So I don't have an OH stretch. Even though this is a carboxylic acid, it would show me an OH. So I could eliminate that. C, and I would eliminate what? Do I see any NHs? No. So the chances are that this has to be B, right? So you can actually use a process of elimination to derive the right answer. How about this one? Where do I start? 1500. Move out to where? Do I have anything? Can I eliminate anything? Can I eliminate anything? I can eliminate B. I don't have anything there that is sp2 hybridized. All right. Do I have anything in the sp region? All right. That might fit. That might fit. That does not fit. So I've eliminated this one and that one. And on an exam, right, if you're at the end and you have to guess, I would much rather have 50-50 odds than a 25% chance, right? If you go to a casino and the house tells you got 50% odds of winning, you're going to leave there with some money, right? If you play right, okay? If you don't leave with money, you're working against yourself actively, right? 50-50 odds are great, okay? So it can either be A or B. All right, excuse me, A or C, yeah. Which one is it? How many people think it's A? How many people think it's C? Why do you think it's C? What's the difference between A and C? An extra oxygen. Now that's getting into the sp2 region, right? Can we really distinguish those without a chart? Probably not. But those carbon-carbon triple bonds are different. What's different about them? One has another carbon chain attached to it, and the other one has a... Do I see anything in the hydrogen region for an alkyne? No. So what's my answer? That's right. Now notice what I can't figure out from an IR spectrum just by looking at the functional group region. I don't know by looking at this if I have 4 CH2 groups or 3 CH2 groups. I can't determine that. I'm just basing this on the functional groups. So I can't get the molecular formula from this type of analysis, okay? And that's okay. You don't need to. Okay? It's all about the functional groups. How about this one? I see that OH, right? That is really, really telling here. That's right. How about this one? Ooh, that kind of looks messy. Notice how complicated the fingerprint region is. Yeah, ignore it. Got an sp2. Does that allow us to eliminate anything? So I'm going to have to use this big broad thing at around 3,000. What's that big broad thing belong to? An OH, but an OH of what kind? An alcohol or a carboxylic acid? That's exactly right. Notice the difference between an alcohol OH and a carboxylic acid. Let's go back. There's an OH, right? Notice it's symmetrical, and it largely stays out of the way of the CHs, unless we had an alkyne, right? It largely stays out of the way of the CHs. A carboxylic acid, however, the OH actually starts to interfere with the CH, and it's really broad and nasty looking. But I'm going to see that, plus I'm going to see the carbonyl, the C double bond O. If you just see that without this, it can't be a carboxylic acid. Chances are you've contaminated your sample with water, and it's broadened everything out. Okay?